Hello and welcome to my video about resonance. So this video is all about resonance in terms of Physics 20. So we're going to talk about three kind of different types of tubes, which if it's a tube it works for a string, works for waves in a pool, works for all sorts of different things. So yeah, let's just talk about different types of resonance. So there are a few different, best thing that you can imagine right now is just take a PVC pipe and you cut it, okay? So if you cut the pipe, it'll just be an open tube, right? That has like a hole on both sides. It's open on both sides. That's what this first situation is, where it's open on both sides. It's basically just a PVC pipe cut, okay? If you take this PVC pipe and you cut it, what happens is when you have open ends on both sides, every time you have an open end, you have what's called an antinode. If it's open, it's an antinode. Okay? And this first one that I'm looking at on the far left is what we call the first mode, and we'll talk about, or fundamental frequency or fundamental resonance. We'll talk about the different overtones later, but for now, that's what that is, so we'll look at it a little bit more later. So anyways, the antinodes are on both ends. And if there's an antinode on both ends, the minimum you can have is to have one node, which is a point of deconstructive interference, whereas the antinodes are nodes are area of constructive interference. So basically there are reflections that happen within the pipe, and when two waves hit each other, they create a standing wave. And we talked about this in the last video about wave interference, but basically over here at all these points here, we have that part's going to be our nodes, and then our antinodes are the points of maximum amplitude, where the string or the whatever sound wave can oscillate the biggest amplitude. Okay, so basically again this is caused by two waves that are meeting at one location, and they're reflecting and they're meeting at the same spot. Well, okay, that's not really the best drawing there, but basically if the two waves are deconstructing at certain locations and constructing at other locations, the green and the purple doesn't really work. There you go. Okay, so antinodes are on open ends, nodes are on closed ends. So now let's take a look over here. This is a closed tube on one side. So you can imagine that if you closed the PVC pipe, now it looks like this second situation. So there's a node anytime it's closed, because it's like you're holding the string tight on one end. You're holding it on one end, and the other end is open, so this would be an antinode then. Okay, now you can imagine here, hopefully if you follow along for a second, that one wavelength, one true wavelength, is from node, skipping a node to get to another node. That is one full wavelength. Okay, so if you imagine maybe drawing one part of the wave, see it goes up, down, and back up again, that is one wavelength. Okay, so going from node to node is actually just half a wavelength, because you have to skip a node to get all the way across. So, and same thing from antinode to antinode, this is going to be only half a wavelength. Okay, but going from node to antinode, that's this section here, this is a quarter of a wavelength. And this is, just that section, right? Short. But if we're going from an antinode to an antinode, that's the half a wavelength we saw at the beginning. And then the most kind of weirdest one, the one that you wouldn't really imagine with a tube, but perhaps it works in another situation, like holding a string on both ends, would have a node on both ends. So a node over here and a node over here. So in this case, it would look like node to node. So I'll just do it from here to here. Okay, so again, that's half of a wavelength. So the length of the tube is half a wavelength in the purple situation for the fundamental frequency, and then quarter of a wavelength for closed and open, and then half again for open on both ends. Okay, then you can see that not only do we have these fundamental frequencies on the far left, but you can have overtones. So this is where you could put, as long as it has two antinodes, if we look at the first one now, as long as it has two antinodes on both ends, like here and here, it doesn't matter how many nodes you have in the middle, as long as there's antinodes on both ends. You can see this happening for all of the different examples. There are antinodes on both ends, and you just slowly add the number of nodes. So this one has one node, this has two nodes, here and here. This has three nodes, here, here, and here. And this has four nodes, here, 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 and here. And you can see this same pattern happening with the next situation, where, again, this always has to be closed, and this always has to be open. So it's closed, open, closed, open. Okay, but then you can imagine the first one doesn't have any nodes inside. The second one has one node, two nodes, three nodes inside. So you can pattern this out, adding half a wavelength every time you add an extra node. Okay, same thing over here. For the purple, it's closed on both sides, and there's one node in this one. There are two nodes in this one. Okay, an interesting way of thinking about this is to think about the concept of resonance as pushing a child on a swing. If you time your pushes well, you don't need to use a ton of force, but it will, if you time it every single time it's at the highest amplitude, i.e. like at the maximum height of the swing, if you push on it at that point every single time, you can increase the amplitude of the swing. So as long as you push on the natural frequency of the swing, you'll make sure that the person is increasing in height. Okay, but if you don't push on the natural frequency, you will not see that increase in height. So you try pushing randomly on a swing, it won't work. But if you push with the frequency of the swing, it will work. Okay, now here's an interesting video that I'm just going to show you guys, just part of it. This is from Geoff Martin, Modes on a String. You can take a look at this. I think I'll put a link to this in the description. But we're just going to look at a section of it here. So let's just look back at this apparatus. Basically, he's got this side stuck and this side stuck, and then he's got a speaker that's going to vibrate the string. Okay? Now he can control that speaker. He can control the frequency of the vibration. And so, yeah, we'll see what that looks like shortly. Okay, so he's going at 5 hertz right now, roughly. So this thing is bouncing up and down 5 times per second. That's 5 hertz. Okay, then he's going to increase the frequency, and you can see that he's getting higher and faster and faster and faster. But what's beautiful is about what's about to happen. He is at like 9 hertz right now, and then he hits that's 11 hertz. So you can see right there 11 hertz, and it's wildly swinging. So we'll go back just a little bit, and you can see that it switches from like 9 hertz 10 hertz, and then it goes boom, 11, and it just expands. So at 10, it's very close to being correct, but it's not quite the same. At 11, it is going wild. Okay, this is perfect because this shows that if you hold it on both sides, then and this is timed right, you can hit the resonance of the string itself. Okay, now we're going to hop forward a little bit more, and we'll be able to see he's going to change it now to higher and higher and higher. So right now it's 11 hertz, but okay, now he's higher than 11 hertz. Now it's going faster than that. And now he hits 22 hertz. Double the frequency, which means half the wavelength. Half the wavelength. So then this string now flips into the second or first overtone, the second fundamental, second mode. Okay, at 22 hertz. Now I don't know if he's able to continue this. I haven't even checked further. Oh yeah, there you go. At 33 hertz, boom. Now it's 3 times the wavelength, or sorry, a third of the wavelength. Okay, and 44, and I don't know if you can do 55, but if you can. Okay, it's messed up for a little bit, goes to 55. He's going to go higher and higher. I think you can get 66 as well. So you can see right away, this is 66 hertz because it's 6 nodes, whereas before it was just 2 nodes. Well, I guess it's 8 nodes instead of 2 nodes. The 2 ends are also nodes. So 1, 2, 3, 4, 5, 6, 7 nodes, whereas at the beginning, 1, 2, 3, 4, 5, 6, 7. Whereas at the beginning, we just had the 2. So we added another 5. Right? We have only 1, 2 at that point. So, like I said, I'm going to link that video down in the description. But we have a couple questions here. And this is, given that the above string is of length 30 centimeter, what is the velocity of the wave through the medium of the string? Now you could have used any one of these different frequencies that we saw, 11, 22, 33, 44, 55, 66, right? But if you use the 11 one, it's the easiest because you can go straight to this situation. We can go to the situation where we have a node on both sides, so length equals lambda over 2. Okay, given that the above string is of length 30 centimeters, what is the velocity of the wave through the medium of the string? Well, basically we need to find we know the length of the string, but we need to find the actual wavelength. So it's 2L equals the wavelength, which is fine, but that doesn't tell us the right answer yet. What we need to do is now use our velocity formula. This is great too, but it also doesn't work yet but until we put the lambda version in there, so the 2L, and now we can finally solve for the velocity. All right, so now we can actually solve for the velocity. So now we're going to plug this all in. So the frequency was 11 times by 2 times by L, which is 30 centimeters. So the velocity in the string is 660 meters per second. So the velocity is actually pretty darn quick going through the string. Okay, let's keep going here and we can hopefully try some of these other questions out. Example number 2, you have an open tube on both ends. Well, if it's both open on both ends, that means our formula is going to be L equals lambda over 2, which perhaps you can't remember it, but if it's open, there you go. Hopefully that makes a little bit of sense. It's open on both ends, so that means there's going to be an antinode on both ends, which means it's half of a wavelength. Okay, so you have an open tube open on both ends of a length that in air, which is the speed of sound there. What is the frequency of resonance that would get amplified by the tube? So basically, what pitch is another way of saying this. So what pitch do you have to sing at or whistle at where it would amplify the tube? It would sound louder because of the tube. Okay, so this is the length of the tube. So we need to find the wavelength. So 2L gives us the wavelength. Now, that's fantastic, but we also need to use our velocity calculation to then rearrange and solve for our frequency. So V over lambda equals our frequency. So it is actually going to be V over 2L is our frequency. So frequency equals, and now we're going to type this in. So 343 divided by, and then in brackets 2 times L, which is 1.2. And so it's 142.9. Just let's see, we got 3 sig digs, so we should just do 143 hertz. Okay, so we solved for velocity, one example, frequency, another example. Let's take a look at example 3. If you have a tube that is closed on one end, okay, closed on one end, and open on the other end, like a water bottle but uniform, then you can cut the tube into make whatever pitch you desire. Given that the speed of sound is that in a dry room, what length must be cut in order to produce a middle C note? So this should look like this, with a node on this side and an antinode on this side. So therefore it should be lambda over 4 equals the length of the string, because what you of the tube, because what you have here is a quarter of an actual wavelength. Okay, you'd have to continue the wavelength back to get the rest of the wave. Okay, so that is our formula there. Now we're looking for the middle note of C. That is our frequency. So we need to figure out what length we need to cut. So we don't know the length yet, but we can work our way backwards. So V equals F times lambda. Okay, now we don't know lambda yet. Okay, but if we solve for lambda here, so V over F equals lambda, now we can plug that lambda back into the blue equation to solve for L. So there's our equation. I'll just rewrite it out over here. So L equals, and actually the F can go right to the bottom, so 4F, V over 4F, so L equals, and so now we can plug this in, 343 divided by bracket, divided by, oh no, that didn't work, 343 divided by bracket 4 times the frequency, which is 265, and so we get 0.323. I think that's 5.8, and this is in meters, so we could simplify this to 32 with 3 sig digs, 32.4 centimeters. Alright, so we've solved for velocity, frequency, and the length. We have never solved for the wavelength, but that's actually honestly easier. We've solved for the wavelength throughout, actually, with different examples like this one and this one, so not too bad. Okay, so we're going to do our last example now, example number 4. Consider a swing of length 3 meters at the playground. If you want to push it in order to produce resonance, at what frequency would you have to push the swing? Assuming no air resistance and friction and all those other things. Okay, so here, I'm giving you the formula a little bit ahead of time here. This is our formula that we're going to use, right? And we want to push it at the right frequency to get the resonance. So this is a pendulum type question, but we're going to find the frequency at which you have to push it to get resonance. So it's more of a conceptual thing using the pendulum idea. The only other formula you need is that frequency equals 1 over period. So using those two formulas together, frequency equals 1 over 2 pi square root L over G. And you could, plug it in exactly like that. Or I'm just going to simplify it to 1 over 2 pi. And then this is just going to be G over L. So this works just fine. Or, some people might prefer it like this. Whatever works. All three of those equations really mean the same thing. So let's plug it into our calculator. I think I'm going to do the second option of those. So 1 divided by, 1 divided by bracket 2 pi bracket times the square root of 9.81 divided by the length, which is 3, bracket, enter. So this tells us the frequency. So the frequency is 0.287 8 hertz. Okay, or if you think about we could also find the period in which you have to push it. But basically, this is how many times per second, so not even once per second, right? So if we just want to find out what this would be in period, to give you some idea, you have to push every 3.5 seconds. Okay, which is this many hertz. So let's just go with 2.9 hertz. All right, so I hope this video helped you understand resonance a little bit better. My understanding is that technically you won't have to do these calculations, but since these couple formulas, blue, green, and purple, are not on your formula sheet, you don't need to be able to calculate them. But you have to understand this concept, and so, the calculations are so easy that you may as well be able to do it. Now, this idea of resonance happens with all types of waves, transverse, longitudinal. So just keep that in mind. It works with everything. So resonance works with strings. It works with swings. It works with sound. Water waves, right? Any type of wave that you can think of, resonance holds some sway over that. So I hope this video helps you understand resonance a little bit better, and good luck.